sheet of charge. So I'll sort of draw it like so if we did this is sort of a view at an angle here, but if we did a side view, the electric field comes out parallel in all directions like this. So what kind of shape would you want to put in there? You want to know what is the electric field right there. What kind of shape are you going to put in here to help you find the electric field at that location? Square? So something like something like that. A cube, right? It's a surface. Anything else? What do you think? A cylinder oriented which way? Like this? But let's take a look at our top view here. This would be our side view, right? Is that right? You understand, we've got a sheet of charge. So if you have a cylinder, right, a cylinder like this, sheet of charge, infinite sheet of charge, then the problem is when you look down from the top, right, it's cutting through the cylinder the way I've drawn on the left here. Is that helpful? Because why not? It's different angles. Your normal to your surface is doing this, right? The normal to the surface is changing. The angle between the E and the normal to the surface is changing. It has to be constant, or you have to integrate, and we don't integrate in here. So it has to be constant. So this one is not going to be very helpful to us. But you can use a cylinder. How do we orient our cylinder so that we can use it? Why was the square okay? Let's go back, look at the square. Let's number the sides, maybe. We've got the top the back, the front, the bottom, the right, and the left. The top. What's the flux through the top? 0. The field lines never penetrate the top. The surface and the field lines are parallel, or theta is 90 degrees everywhere. See that? The front. Same thing, right? The bottom, the back. All 4 of those sides are a very similar situation. The flux is 0. The field lines never penetrate any of those surfaces. The left and the right, we have flux, right? And it's okay to use those surfaces because E is constant over the surface and theta is constant over the surface. So we can use E times A times cosine 0 degrees, right? Okay, so how can we orient our cylinder? We can orient, so let me fix this. I shouldn't say it doesn't work. It doesn't make it easy for us to do Gauss's law, right? If you really wanted to do a hard integral, you could use this orientation for your Gaussian surface. But our point is we're trying to make it easier for ourselves. Okay. So, maybe does not work easily. That's okay. Does not work easily for Gauss's law. There we go. That's better. More accurate. Okay, so how would we do it? We would orient it this way, right? The electric field does something like that. We say EA cos theta over the left plus EA cos theta over the sides plus EA cos theta over the right has to equal Qn over epsilon naught. And the sides, there's no flux, right? That's 0. Because cosine of 90 degrees is 0. And the left and the right, this is going to be E times the area of the left E times the area of the right. And so what do we end up with? We end up with 2EA, where the electric field is 1 over the area 2 epsilon naught Qn over the area. And what is Qn over the area? This area is going to intersect that charged sheet. And this Qn is the charge on this purple area that's intersecting the sheet and the cylinder, right? The intersection between the cylinder and the sheet. So that charge divided by the area should be a constant anywhere on that sheet if it's uniformly distributed charge, right? That's the charge density, charge per unit area anywhere on that sheet. Just like we use charge per unit length, right, for a long cylindrical shape, we use sigma. Charge per unit area. And we get the electric field as sigma over 2 epsilon naught. So given the charge density on this sheet, every square meter of this sheet has 3 coulombs of charge, something like that, right? Then we would know the charge density. Then we would be able to figure out the electric field from that sheet. So this is kind of an interesting result. What's the first thing that jumps out at you when you look at this result? You think the electric field would be stronger close to the sheet, further away from the sheet? Where's the distance to the sheet in our answer? It's not there, is it? So what does that mean? Doesn't depend on the distance. Maybe we just made that assumption. When I said those electric field lines come out parallel, what does that mean? It means the electric field never changes as we move away from the sheet, right? Because the density of the electric field lines, remember how do we draw electric field lines? The density of electric field lines is proportional to the strength of the electric field. So if the field lines never get further apart, the field never gets any weaker, right? It stays the same. So this is because the sheet is infinite. If you're close to the sheet, the charge that's far away is kind of canceling out. If you're doing this, here's your sheet of charge. And if you're here, remember this is a vector quantity. Electric field's a vector quantity. So the charge way up here at the end, maybe I'll use a color code here. The yellow charge up here is creating an electric field that points this way, right? And the charge down here is creating an electric field that points this way. So those two are almost completely canceling each other out. They have very little effect. So the stuff that has a lot of effect is in here, right? Oh, you should use a different color. This stuff has a big effect, right? And you're close to it, and it has a big effect. And the stuff that you're far away from has very little effect because it's all canceling out because of the angle. If you're out here, this one right, the yellow one has a small effect, right, a smaller effect, but it's pushing, it's in the direction to the right. The blue one is also more to the right. And the stuff in the middle here is much smaller like that, right? So you have to scale these down a little bit. And you add them up and you get the exact same thing you got. So your net should make this one a little smaller over here. So it's the same in both cases. Right, independent of distance. You see how that works out? Question, Gabe? There is, typically we're interested in the electric field at a single point. We draw one of our Gaussian surfaces at that point, and we draw our Gaussian surface in such a way that E is constant over that whole surface. If E is not constant, because you can't, if you have a less uniform distribution of charge, or I should say a less symmetric distribution of charge, then you can't draw a Gaussian surface where E is constant over the whole surface. So you wouldn't use Gauss's law because it's an ugly integral to solve it. It still works, but it's not going to help you get the right result. It's not going to make it easier for you to get the right result. So the answer is, typically we're looking for the electric field at a point. We draw a Gaussian surface with one of our surfaces at that location at that point, and we draw it in such a way that the electric field is constant over the entire surface, or we can't use Gauss's law in this class, because then it would be a big integral.